All right, so as you guys know, atoms, they have their protons in the nucleus. So the nucleus is positively charged, and then you got your negative electrons flying around the nucleus. Okay, so that's something that we already are familiar with. Now, the new term that we're going to be learning about is something called ionization energy. Okay, ionization energy. I like to abbreviate it just IE. And so if you guys see that as you guys are doing your workbook problems and whatnot, or as I'm lecturing, if I say IE, it's referring to ionization energy. Just a heads up, when you guys do your exams and the AP test, don't write IE, just write ionization energy. But for the sake of brevity, we're going to use IE to represent that. Okay. And ionization energy is a pretty simple concept, okay? Basically, it's the amount of energy you need to put into the atom. So if let's say that we're shooting in energy into the atom, the ionization energy is the amount of energy it takes to basically remove one of the electrons. So to get one of these electrons to leave the atom. Okay, that's what we call ionization energy. It's the amount of energy it takes to remove an electron from the atom. Okay. All right, so there's two concepts that come with that. The first is this one right here. The farther an electron is from the nucleus, the lower the ionization energy. Basically, it takes less energy to remove an electron that is far away from the nucleus. Okay. So the further an electron is from the nucleus, the easier it is to remove it. So we say it has a lower ionization energy. Okay. And the second concept that comes with it is basically with the nuclear charge, which is basically how many protons there are. So the more protons there are in the nucleus, the higher the ionization energy. Okay, so that's going to require more energy. Okay, so the more protons there are, the more positive energy there is in the nucleus, the harder it is to remove the electron. It takes more energy. All right, any questions on ionization energy? This is just a basic preliminary information. It actually gets a little bit more complicated from here, but I wanted to make sure that you guys understood the basic concepts. All right, so we're going to be taking some time to talk about energy now. And so we're going to be, if you guys have your AP equation sheet, if you guys take a look at the very top, the one that says atomic structure like this, we're actually going to be using this box right here, atomic structure, for this unit right here, okay? So if you guys have that handy, you guys might want to pull it out. If not, I'll have all the equations up there for you. But just know that for Unit 7, we're going to be using this part right here, atomic structure, and obviously including these variables right here. Okay, so we're going to be talking about light, because light is how we usually, what we're talking about when we talk about ionization. When we talk about putting energy into an atom, we're usually talking about putting light energy into the atom. Okay, so if you took physics, this is going to be a review, but if not, it's okay. We're going to go over all the information that you need from here, okay? All right, so light has a couple properties that we need to talk about. The first property is that light has a constant speed. It's 3 times 10 to the 8 meters per second, and that's actually on your AP equation sheet. Speed of light, C, is 2.998, but you can just round it to 3, okay? So C is 3 times 10 to the 8 meters per second. Okay, so that's the speed of light. Light always moves through a vacuum at 3 times 10 to the 8 meters per second. Okay, so you might be familiar if you know E equals mc squared. That's the same C as this one right here. Where were we? Okay, yeah, so light travels at 3 times 10 to the 8 meters per second. You will always see that as the variable C. The next variable you need to know is something called wavelength, and it's exactly the way it sounds. Light moves in waves, so it goes up and down like this. And so basically the distance, the length between the waves, that's what we call wavelength. We use this symbol right here. It's called lambda. It's a Greek alphabet thing. You guys don't need to know what it's called. But if you ever see a symbol that looks like that, it's kind of like a tree that's falling. Just know that's referring to the length of the wave, okay? And then the second one is the frequency, basically how frequently the waves come, okay? And that's this right here. It looks like a V. This is mu in Greek letter, but it's like a V with a little like bird head next to it, okay? So we're going to be talking about those three variables frequently. So just make sure that you're familiar with them. I believe they're all on your AP equation sheet. They actually combine to form an equation right here. So just know that they're available right there for you as well. Okay. All right. So let's talk about wavelength. So light has there's a big range in how long, the distance between the waves. And so depending on the type of radiation or light that we're looking at, they can have a very long length. So if we take a look at the extreme ends, radio waves, the distance between the waves can be over 1,000 meters. But then when we get to things like X-rays and things like that, it can be nanometers, angstroms, 10 to the negative 10. It could be very, very small. Okay, so for this unit, you're going to have to be very comfortable working with exponents, negative exponents, and things like that. So we're going to do a little bit of practice. I want you guys to try 7.1. I want you to convert 650 nanometers into meters using scientific notation, okay? You have your conversions right here, so take a second to try that out, and then we'll go over that in just a second. Alrighty, guys, so let's take a look at 7.1, and then we'll go over together. So we got 650 nanometers. Now, if you guys take a look at our conversion factors right here, we have nanometers as 10 to the power of negative 9, okay? So if it's 650 nanometers, we can do 650 times 10 to the negative 9, okay? So far, so good? Okay, we still need to convert to scientific, but what's up? No, you do not. Yeah, great question. You do not need to memorize them. All right, so we need to turn to scientific notation, which means we need to move the decimal until there's only one number in front of the decimal. So what we're going to do is we're going to take the decimal point, which is right here, and move it twice to the left. And that way we get 6.5. Yeah, I mean, it's 1 times 10 to the negative 9, but we can just, if we multiply 650 by 1, that's 650. So you can just plug it right there. All right, now, since we moved the decimal point, we need to change this exponent right here. Now, if you move the decimal point to the left, so if you write the decimal to the left, what's going to happen is your exponent, the value is going to go up. Okay, now, that's a little bit confusing when we're working with negatives, because if you think about up, you think about 9, 10, 11, right? But if you look at it, it's negative 9, right? So since we move the decimal point twice to the left, the exponent is going to go up twice. So going up from negative 9 would be negative 8, negative 7. So it's going to be 10 to the negative 7 meters, okay? So just keep that in mind. The negatives make the decimal moving a little bit complicated. But just know decimal to the left, exponent goes up. Decimal to the right, exponent goes down. Okay, and just keep in mind the negative numbers. I'll be honest, I sometimes get confused still too. So just keep that in mind. What's up? Oh, you're able to use calculators, yeah. It would be a nightmare to do this by hand. All right, any questions? Okay. Just make sure that you're comfortable with the scientific notation, working with exponents and things like that, because for this unit, we will be looking at this a lot. A lot of our calculations will involve this. Okay, so let's move on. So let's talk about the properties of light a little bit more. So one of the properties we talked about is frequency, and it's basically the cycles per second, basically how many waves come per second. Now, there's a couple units of measurement we use to measure it. The first is hertz, which we abbreviate as Hz. You guys might have heard that when it comes to like the radio, right? Talks about hertz, megahertz, things like that. It's because of the frequency of the radio waves. Now, 1 hertz is equal to 1 wave per second, and the way that we represent the units of measurement for waves per second is just seconds to the power of negative 1. It just means per second. Okay, so if you ever see something like this, 650 seconds to negative 1, it equates to 650 waves per second. Okay. Just keep that in mind. That's just a unit of measurement for measuring frequency. How many waves come per second? All right, so we're going to be taking a look at this equation right here, and I believe that's the first one on your AP equation sheet. And what this equation tells you is it describes the inverse relationship, the opposite relationship between wavelength and frequency, okay? So I know that waves, radio waves, light waves, it's a little bit hard to visualize, but hopefully we've all been to the beach, right? We live in Long Beach, and we've seen the waves there. And so we're going to use the waves that we see at the beach to kind of help us visualize the relationship between wavelength and frequency. Okay, so let me show you another one of my amazing drawings. Okay, let's say that this is you. Okay, and you're at the beach. Okay, so this is the beach and this is the water. I'm gonna make it blue so it's more realistic. Okay, so this is you at the beach. You're in the water. Okay, now I know it's amazing, right? Now let's say the waves are coming towards you. Okay, and then you're getting hit by these monster waves that are taller than you. Okay. Now, these waves, if you've ever been in the water and got hit by waves, they have energy, right? And you feel the energy as you get hit by them. Okay, so let's take a look at these waves. Let's say there are multiple waves coming at you. Okay, and let's say this is the wavelength, right? This is the distance between each of the waves. Now, if the wavelength is long, if it's very spread out, what that means is, so if as the wavelength goes up, okay, the energy is going to decrease, right? Because if there's a big gap between the waves hitting you, you're not going to be getting hit with as much energy, right? But let's say that you're, again, this is you in an alternate universe. This is you in a parallel universe. Okay. But this time, instead of a long wavelength, let's say that you have a very short wavelength. Okay. So you're getting hit by these waves and the wavelength is very, very short. Okay, so as the wavelength goes down, what's going to happen to the amount of energy you're hit by? It's going to go up, right? And so that shows the inverse relationship between wavelength and energy. Okay, the longer the distance between the waves, the less energy they have, and the shorter the distance, the more energy they have. Okay? Yes. Well, if we assume that they're the same height, I know that my picture's not that great, but let's assume same height. Okay. But if they're closer together, you get hit by more energy. Okay. Now, we also bring in the other variable. So let's take a look at the frequency. Okay. So if the wavelength is long, what happens to the frequency? Does it go up or down? It's going to go down, right? Because you're going to get hit less frequently. But as the wavelength goes down, what's going to happen to the frequency? It's going to go up. Okay, so just keep that in mind. That's just the relationship. The equation we looked at, that's what it's telling us. It's telling us as the wavelength increases, the frequency decreases, which means you get less energy. And as the wavelength decreases, the energy increases and the frequency increases. Okay. So if you're ever stuck thinking about this, just think about you on the beach. What happens if the waves are frequent or if the waves are not frequent? The waves are far apart or if they're close together. All right, any questions on frequency, wavelength, energy? Probably not too bad. All right, that kind of leads us into this diagram. You guys might have seen this in your other science classes before, but it's basically all the different types of light that there are and their relationship with the wavelength and their frequency. Okay, so all the way at the end, the weakest, the lowest energy, so this is the lowest energy waves are radio waves. Okay, now if you guys take a look at the numbers, the radio waves, they have very big wavelengths. Okay, the distance between the waves are really big. Okay, and then as we go down into higher energy, so increasing energy, you're going to notice the wavelength goes down, right? The distance between the waves go down. So next we got microwave, we have infrared, and then we have the part that we like, where you can see the actual colors. Okay, and then after that's ultraviolet, which is more energy. This is why you get sunburns and you get skin cancer if in the sun too much. X-rays, which is why you wear a lead plate when you go to the hospital to get an X-ray. And then we got gamma rays, which will turn you into the Hulk, right? So increasing energy as the wavelength goes down. Okay, you guys see that relationship, right? Okay, now if we take a look at the frequency, again, the frequency is very high here. The number is very big, and the frequency here is very low. Okay, so that's just another way of looking at, what is it? The energy, the wavelength, and the frequency. Okay. Right now, just giving you guys a heads up, you guys might see a question that requires you to analyze a chart like this on the AP test. We've seen it before. And so we're going to do a problem like that. Okay, you do not need to memorize any of these. I have no idea what the wavelength and the frequency of these light things are off the top of my head. And I'm doing fine in life, so you guys will be fine. You will always be given these numbers, okay? All right, so we're going to try 7.2. Okay, 7.2. What's the frequency of light that has a wavelength of 10 micrometers, and what type of light it is? Okay. So in order to do this, we're going to be using the equation that we just had. C equals the wavelength and the frequency. And again, we get this from our AP equation sheet. And it's going to be the second one. Sorry, I think I said first one. The second one right here. All right, so first thing we want to do is we want to figure out, since this is probably variables that are unfamiliar to us, we want to figure out what we're looking for. Okay, so in this question, it's asking us to find frequency, right? So if you guys remember, frequency is going to be this one right here, mu, the V with a neck. Okay, so we are looking for this one right here. Okay. So if you guys want to, you guys can rearrange this equation to isolate mu. So to do that, we just need to divide both sides by the wavelength. So mu, the frequency is equal to C divided by the wavelength. Okay, if you're the type to just kind of plug it in and solve for it, that's totally fine as well. I just personally like to do this, so I'm going to do it this way, but you guys can do it however you like. All right, so far so good, guys? Okay. Next, we're going to plug in our number. So, well, it tells us that our wavelength is 10 micrometers. Okay, so this little U with a long left side. So we're going to go up to our chart and take a look at what this means. So we're going to take a look at our chart, and then, oh, it's not here. Oh, it is right there, right here, micrometers. Micrometers is right here, and that's 10 to the negative 6. Okay, so 10 to the negative 6. So our wavelength is going to be, bottom, 10 times 10 to the negative 6 meters. Okay. So far, so good? Okay. Now, the reason why we converted it to meters, 10 to the negative 6 meters, is because we need to use C, right? And if you guys take a look at your AP equation sheet, it's going to be 3 times 10 to the power of 8 meters per second. And that's why we needed to convert the micrometers into meters. It's because we needed to line up these variables. Because if they cancel out, what are you left with? You're left with per second, which is waves per second, which is what frequency is. Okay, so the math here is pretty simple. After we do all that, it's going to be 3 times 10 to the 8 divided by 10 times 10 to the negative 6. All right, so I will give you guys about 2 minutes. I think we learned how to do scientific notation the first unit, but just to kind of see if you guys are comfortable doing this, I'll give you guys about 2 minutes to try this out. Check with your answer or partner, and then we'll go over it together. How to do that? Okay. And the reason why the TI calculators are a little bit better than the scientific ones for this is because you can just plug in these exponents. I swear the AP test is like sponsored by Texas Instruments or something like that. But anyway. All right. So if you guys do not have the TI calculators, you guys got to do this manually. And it's pretty simple. First thing you want to do is you want to take the normal numbers and you want to just do the operation that it tells you to do. So you would first do 3 divided by 10. Okay. So for 3 divided by 10, you're going to end up with 0.3. Okay. All right, next, we're going to work with the exponents. So 10 to the power of 8 and 10 to the power of negative 6. Now, if it's a division sign, what you have to do with the exponents is you need to subtract them, okay? So you're going to do 8 minus negative 6. Okay, so that's negative, negative. That's going to be 8 plus 6. And so you're going to end up with 0.3 times 10 to the power of 14. Yes. 3 times 10 to the 8. Yeah, that's the speed of light for C. It's on your AP equation sheet, 2.99 times 10 to the power of 8, but you can round it up to. All right, now we're not done yet because we need to do this in scientific notation, right? And so what we have to do is we need to move the decimal one time to the right, okay, to turn this into 3. But if we move the decimal one time to the right, we need to change the exponent. Okay, so the value is going to go up, and then it's, wait, sorry, it's going to go down, my bad. The value is going to go down, and it's going to be 10 to the power of 13. And the unit of measurement is going to be per second. Okay, sorry about that, guys. Okay, so just remember, if the decimal moves to the right, your exponent is going to go down. If you move your decimal to the left, the exponent is going to go up. Okay, but this time we moved it to the right, and so that's why our value went down from 14 to 13. Okay, but if you have a Texas Instruments calculator, you don't even need to do all that. You can just plug it in with the parentheses, and you can thank your parents because they saved you so much time and headache. All right. Any questions on how to find the frequency? Hopefully the calculation's not too bad. We're going to do another example together in a second, but let's finish the last part of the question. The last part of the question is, what type of light is this? So we're going to take the frequency, which is 10 to the power of 13. And what we're going to do is we're going to go to our scale or our chart, and then we're going to figure out what type of light has frequency around that number. So we're going to go up, and we're going to take a look at this part that says frequency, which is going to be this bottom part right here. And we're going to look for 10 to the power of 13. 10 to the power of 13 is right here. So yeah, if you got infrared, great job. That's exactly how you do it. Okay. All right. You guys think you try one on your own? Okay, no response, but I'll assume that I'll take that as a yes. Okay. Let's do 7.3. I'll give you guys about 3 minutes. You can try this one on your own. Okay, this time you're looking at wavelength, and then they give you the frequency, and then you got to figure out what type of light it is. Okay, so try that out, guys. Check with the person next to you, and then we'll double check our answer, and that'll be it for today. Alrighty, guys. So for the wavelength, 5.5, 5.4 times 10 to the negative 7 meters, and that gives you ultraviolet light. Okay. All right, any questions on light, speed of light, wavelength, frequency? You guys all good? All righty.